everyone. My name is Alexander.
Hello, everyone. My name is Kevin.
And I'm Rachel.
And I'm Lorraine.
We are Group 28, and I'm here to present to you our traffic sign recognition project using deep learning. So our table of contents include, we'll start off with the problem, why we're doing this project, and then data processing, demonstrate the model, and then talk about our results. So here's what's going on. The autonomous vehicles market is growing rapidly. As shown in the chart on the left, it is projected to exceed $2 trillion by 2030. But to reach that scale safely, these systems need to handle real-world driving conditions reliably. On the right hand, we see the challenges. These graphs come from the Cure TSR benchmark, which has tested traffic sign recognition models under increasingly difficult visual conditions, things like blurs, shadows, dirty lenses, and rain. The x-axis is the challenge severity, and the y-axis is the accuracy. Notice how almost every model starts near perfect accuracy on clean data, but performance drops sharply as the scenes get more and more complex. In real life, signs are often partially obscured, damaged, or poorly lit, exactly the conditions where these systems struggle. This gap between clean benchmark data and real-world complexity is exactly what our project addresses, developing a more robust traffic sign recognition pipeline that can perform well under challenging real-world driving conditions. And this is why for our data, we're using the TSRD dataset, which contains over 4,000 labeled images spread across 58 classes, with each image containing only one traffic sign at a close-up view. The data is also organized by class and the images are sorted by class. But most importantly, we're using the TT100K dataset, which contains 100,000 labeled images spread across 221 classes, with each image containing multiple traffic signs at the street view. The data is also pre-split into training, testing, and validation, and the image annotations contain bounding box coordinates and shapes. As you can see here, although the TSR dataset only contains one traffic sign per image, there's also varying lighting, shadows, and obstacles, making it perfect for training the early stage models. However, for our final model, we will only be using the TT100K dataset, as it contains more obstacles, distractions, and need for localization, thereby simulating more complex real-world driving scenarios.
We began data processing by extracting the TT100K dataset. It contains 3 images along with an annotations file that specifies the location and class of multiple traffic signs in each image. The traffic signs are small and often surrounded by cluttered backgrounds such as cars, buildings, and trees, making them hard to detect and lowering classification accuracy if used directly. To address this, we used the bounding box coordinates from the annotations file to localize each traffic sign as shown by the green outlines in the top right image. We then crop each sign into a clean focused image for classification. To make our dataset more robust, we applied augmentation such as rotating, flipping, and altering colors. This increases diversity and helps our model handle variations in lighting and camera angle, hence improving its ability to generalize to real-world conditions. The original dataset was split into 61% training, 6% validation, and 31% testing. To allocate more data for hyperparameter tuning, we swapped the validation and test sets. Another issue we encountered was inconsistent class distribution across the dataset splits, where some classes were present only in training or only in testing. To ensure fair and accurate evaluation, we kept only the 96 classes present in all 3 datasets. While this improves consistency, it also narrows our model scope to those common classes. With the data cleaned and organized, we then passed it to our final model architecture.
Moving on to the model part of the presentation, we'll start with the general architecture of Inception ResNet V2 model. It's a very deep convolutional neural network, which includes around 55.9 million parameters and 164 layers. The simplified architecture of the model can be seen in figure 8 in the red contour, and it essentially consists of a stem, which does the initial processing of the image, as well as the combination of inception ResNet blocks and the reduction blocks with a classifier on top of it. It is a valid network for the goals of our project, as it offers a combination of inception blocks and residual connections, which allows for a more high-level feature extraction for a large data set. Using it for transfer learning is also beneficial, as it reduces the computational costs whilst not sacrificing the accuracy of the results. To implement the transfer learning, we load the pre-trained ImageNet model and replace the original classifier with our own classifier, which consists of 2 fully connected layers and a dropout layer. We then freeze the feature extraction part to take advantage of the optimized weights. After training our custom classifier on the TT100K dataset, we want to further tune our model. And this can be completed by gradually unfreezing the feature extracting part of the model, therefore opening more ways to be trained. Although this increases the computational costs, it also allows us to further optimize the pre-trained weights to specifically deal with traffic sign recognition. The unfreezing is completed in 3 steps, and the changes in the number of trainable parameters can be seen in table 1. We full unfreeze the feature extracting layers at epoch 8.
I can see here we are first reorganizing the data set and then splitting it into testing, validation, and training. Now we're training the model over 15 epochs, as you can see, and graphing the results. And here's our testing block. We're going to run the testing. There you go.
Now, let's talk a bit about quantitative and qualitative results. Based on the test results, our model reached an accuracy of 81% with cross-entropy loss of around 1. However, our model was able to reach a higher train and validation accuracy of around 97%. We also calculated several values from the confusion matrix, and with that, calculated the precision, recall, and F1 score. Both precision and F1 score proved the high accuracy of the model despite possible class imbalances. However, the 100% recall caught our attention as it contradicts the moderately high average false negative rate. This may be due to class imbalance, since some classes only had one image, while others had many more. To overcome this, we have implemented data augmentation to produce more images for smaller classes in hopes of reducing class bias. Now on to qualitative results. Based on the loss and accuracy plots from training and validation, accuracies began to plateau and remained convergent starting at epoch 12, demonstrating that our model was well trained with the appropriate set of hyperparameters. It should also be noted that our plots reflected the impacts of unfreezing trainable parameters in the pre-trained models at epochs 4, 6, and 8, by drops in loss curves and jumps in accuracy.